Unit 3, Stoichiometry. Simple stoichiometry, that is, calculations based on balanced equations. Remember the key term, balanced equations. Let's see how it's done. Let's look at a balanced equation. In this case, P4O10 plus 6 H2Os yields 4 H3PO4s. Now, according to the equation, we're being told that if one molecule of this is present, it will react with 6 molecules of water, producing 4 molecules of phosphoric acid. Or you might look at it another way. After all, the mole is a number. So a mole of P4O10 will react with 6 moles of water to produce 4 moles of phosphoric acid. That's right. Now, on basis of that, if we have 3 moles of P4O10, how many moles of water are we going to need to complete this reaction? Well, look at it like this. It's going to need 18 moles because 3 moles of P4O10 will require water on a 6-to-1 mole ratio. Look at your equation. That is called our mole-to-mole ratio, or it may be referred to as a stoichiometric ratio. A stoichiometric ratio. Now, the stoichiometric ratio is a relationship which exists in a balanced equation. The ratio is the moles of unknown to moles of known are given. In other words, it's what you're looking for over what you're given. How many moles of phosphoric acid would be produced if we started with 3 moles of P4O10 and had ample water? Well, look at it like this. We are given 3 moles of P4O10, and we're looking for phosphoric acid. The ratio is 4-to-1. 4 moles of phosphoric acid is produced when 1 mole of P4O10 reacts with ample water. So we take our 3 moles, multiply it by this, and that tells us that we would produce 12 moles of phosphoric acid. 12 moles. Remember now, this is your stoichiometric ratio. But what if we were dealing with grams? What if we weren't given moles? We were given grams. Well, let me show you the way it works. Let's take a situation in which we have 21 grams of P4O10, and we have plenty of water, and we want to know how many grams of phosphoric acid would be produced. This is the way it works. We start with a known quantity of whatever. We convert that known quantity to moles of what we have. We get from moles of what we have to moles of what we need. And then, if necessary, we convert those moles of what we need to quantity of what we need. The question is, how do we do this? And the answer is the stoichiometric ratio. Yeah. The stoichiometric ratio is the key. Well, let's work some problems. What weight of phosphoric acid could be produced when 3.6 grams P4O10 react with excess water? Okay, we're going to start with our 3.6 grams of P4O10. Now remember, we're going to look for H3PO4. That's what we're looking for. That's our goal. So we start with the quantity of what we're given, which is the P4O10. That's our 3.6, and we convert that to moles by multiplying by 1 mole over 284 grams, the molecular weight of P4O10. Now we are at moles of what we started with, or moles of what we're given. Now let's get to moles of what we're looking for. Do you remember how to do that? Sure. That is the stoichiometric ratio of 4 to 1. 4 phosphoric acids to 1 P4O10. So we're at moles now of what we're looking for. Now we want to go to the quantity of material that we're looking for. So to convert from moles to mass, we multiply it by the gram molecular weight, 98 grams per mole. And when we do this, our answer comes out to be 5 grams. It's just that simple, but there is a roadmap of how. Let's try this one. Calculate the weight of copper needed to react with 10.3 grams nitric acid. In other words, what we want to know is what weight of copper is required to react with 10.3 grams of nitric acid. All right, let's have a look at it. We start with what we're given, which is our nitric acid, 10.3 grams. We convert that to moles, 1 mole over 63.0 grams per mole. Now we're at moles of nitric acid. Let's go to moles of copper. And it is a 3 to 8 mole ratio. Now we are at moles of copper. We exit on the quantity of copper by multiplying by 63.5 grams per mole, which is the atomic weight of the gram atomic weight of copper. And this is going to give us 3.89 grams as our answer. There's a nice pattern of how you go about solving it. Look at the logic of it. Be sure you understand. Got it? Let's let you try this one. In this problem, we want to know what mass of nitric oxide will be produced. If we're going to allow 14.5 milligrams of copper to react with what we will call an excess of the nitric acid. Now let's start with 14.5 milligrams. Yes, if you wish, you can start and convert those milligrams to grams. But if you don't mind, I'm going to leave them at milligrams, and I want to show you something. Times 1 mole. We're talking about copper, and the gram molecular weight of copper, the gram atomic weight of copper, is about 63.5 grams per mole. Now, we're going to go to our mole-to-mole ratio. It's what we're looking for, which is the nitric oxide, over what we're starting with, which is the copper. So it's times a 2 to 3 mole ratio times the molecular weight of the nitric oxide, which is 30.0 grams per mole. Now, look, grams are going to cancel grams. Moles are going to cancel moles. And my answer is going to come out in milligrams. And when I work this through, I get the answer to be 4.57 milligrams. I want to set this up again and show you a different way to cancel your units. We have 14.5 milligrams times 1 mole over 63.5 grams. I like to stop at this point and cancel my units as a rule. These grams here are going to cancel these grams here and leave me with an expression called millimoles. But don't let that disturb you. Times a 2 to 3 mole ratio times 30.0 grams per mole. And moles here will cancel moles here. And I am going to be left with my units of milligram. And it's going to give me still 4.57 milligrams. Now, you might want to, if you're at all uncertain about how to do this, then you might want to hold off on doing that and just convert your milligrams to grams and go from there. And then convert back. It's up to you. There are several ways you can go about working these kinds of problems. There are times you're going to run into a situation in which several equations are involved. And when several equations are used, there is a key that you have to understand, and that is the quantity produced in one equation is the quantity used in another. Let me give you an example. Here we have two reactions. We have the reaction of P4O10 with water producing phosphoric acid. Then zinc is allowed to react with the phosphoric acid produced in equation 1 to produce zinc phosphate and hydrogen. Now, folks, what connects these two equations? Well, the thing that connects them is the phosphoric acid, yeah. Because the quantity produced in the first equation is the quantity that is consumed in the second equation. Now you're looking at that and saying, but there's a 4 in front of the phosphoric acid in the first one, and there's a 2 in front of the phosphoric acid in the second one, so it has nothing to do with it. The 4 and the 2 have no relationship with each other. It is the quantity that is produced in the first is equivalent to the quantity produced in the second. The 4 from the first equation talks about the relationship with the other two compounds in that first equation. The 2 in the second equation talks about the relationship, the mole-mole relationship in the second equation. The mole-mole relationship from the first equation doesn't have anything to do with the mole-mole relationship in the second equation. You got the idea? What weight of zinc is needed to react with the phosphoric acid produced if 10.0 grams P4O10 is consumed in the process? And we're talking about the same process that we were using previously. Here I am showing you the balanced equations and also the connectors between the two equations. We're going to start with 10 grams of P4O10, and what do we want to know? The mass of zinc. So we've got to go from P4O10 to something, and then from that something to zinc. And the something that we've got to get to is the H3PO4. That is our connector. So we start with 10 grams of P4O10 and get to moles of P4O10 by multiplying by 1 mole over 284 grams. Now we need to get to moles of phosphoric acid. And to do that, we use the mole-to-mole ratio or the stoichiometric ratio. And that's 4/1. Now we are at moles of phosphoric acid. And folks, that moles of phosphoric acid in the first equation is the same number of moles of phosphoric acid that we're going to consume in the second equation. So we are already at the phosphoric acid in the second equation, so we just go to zinc. And the ratio between the phosphoric acid and the zinc is defined in the second equation as 3 moles of zinc to 2 moles of phosphoric acid. Now we are at moles of zinc. We can exit on quantity by multiplying by 65.4 grams per mole. And that gives us our solution of 13.8 grams of zinc. Now look at this very carefully. Be sure you understand how we made that transition. In this problem, we're starting out with 3.8 grams of zinc. And we want to find the weight of P4O10 that's going to be needed to produce enough acid produced here and consumed here to react with that 3.8 grams of zinc. And this is the way it works. We start with our 3.8 grams of zinc times 1 mole of zinc over 65.4 grams times now we're starting with zinc, and we want to go from zinc to phosphoric acid. So that is times a 2 to 3 mole ratio. Now we are at phosphoric acid, which means we're right here. And we want to go from phosphoric acid right here all the way over to P4O10. And our mole to mole ratio there is 1 to 4. Then we have the molecular weight of P4O10, which is 283.9 grams per mole. And our units cancel, moles, grams cancel grams, and we're going to be left with grams of P4O10. And I get that answer to be 2.7 grams. Now, have you got the idea of how to handle multiple equations? There are some additional calculations that we need to do regarding equations. One is percents and percent yield, and the other is limiting and excess reagents. Let's start with percents and percent yields. It's been my experience that very often I have students who are excellent problem solvers unless I put a percent in the problem. And then they get really confused. Now, percents are commonly used in chemistry because we use them to describe reagent purity, talk about percent yield, we talk about all kinds of things. Let me show you an example. You need to have sufficient phosphoric acid available to react with 6 grams of zinc. But the P4O10 that you use to make the phosphoric acid is only 47.2% pure. So the question becomes, how much of the impure P4O10 should you have on hand to make enough phosphoric acid? And here are your two equations. Well, we're going to start with the zinc. We have 6 grams of zinc times 1 mole over 65.4 grams. That gives us the moles of zinc. Now we're going to go to moles of phosphoric acid, and that's times a 2 to 3 mole ratio. But you have to understand now the phosphoric acid that you're producing in the first equation is the same as the phosphoric acid that you were using in the second equation. Now you're at the phosphoric acid in the first equation. Let's get to P4O10. And that's 1 to 4 ratio. And now you're right here. So let's exit on quantity, 284 grams per mole. And that tells us that we need 4.34 grams of pure P4O10. So how much impure P4O10 do we need to use? And the answer is I don't know. So I'm going to call it X. And what I do know is that 47.2% of X has got to give me 4.34 grams of working reactant P4O10. So I divide both sides by 0.472 and I get X is equal to 9.2 grams of impure P4O10. Got the idea? Good. In the single replacement reaction of copper with silver nitrate solution, 1.2 grams elemental silver forms from the reaction of 0.51 grams of copper wire with excess silver nitrate solution. We want to find the percent yield. Now here's the equation. We're starting out with 0.51 grams of copper wire, putting it in plenty of silver nitrate solution, and we're producing elemental silver, precipitating out and leaving cupric nitrate solution in our products. And we want to find the percent yield. So here we go. We're going to start with our 0.51 grams of copper. We're going to go from copper to silver. But first, we have to convert it to, that's right, moles. 1 mole over 63.5 grams gives us the moles of copper metal. The stoichiometric ratio that we have is 2 to 1 to go to metallic silver or elemental silver. Now we have moles of elemental silver. Let's convert it to mass. Times 107.9 grams per mole. Tells us then that the theoretical yield is 1.73 grams. In other words, we should produce 1.73 grams of elemental silver. But we didn't. We only produced 1.2 grams of elemental silver. And we need to find the percent yield. So we take our 1.2 grams of what we got, put it over the 1.73 grams that we should have had, times 100, and that's going to give us a yield of about 69.2%, depending on where you round things off. This then is our answer, 69.2%. Where did the rest of it go? Well, it could be that you did not have contact between the molecules. It could be that you made an error in measurement, particularly weight in drawing something out. It could be that you lost some of it somewhere. There are all kinds of reasons for this. That is a good study for lab to do. Limiting and excess reagents. Limiting reagents are just as the name implies. They're the reagents that limit how much reaction product you're going to get. Because limiting reagents are those substances that are consumed entirely. That's what you're going to run out of. Excess reagents are those reagents that you're using in a reaction that aren't all used up. In other words, they're those substances consumed only in part. Here, let me give you an analogy. The analogy has to do with building cars on an assembly line process, if you will. Now suppose you're building cars, maybe cars, not cars this old, but you get the idea. If you have 20 tires and 14 headlights, how many cars can you construct? Well, if you have 20 tires, you can construct 5 cars, right? If you have 14 headlights, you can construct 7 cars, right? 2 headlights to a car. So you're going to run out of tires after you've constructed 5 cars. So what is your limiting reagent? Your limiting reagent happens to be the tires. Not because that's the number you have the lesser of, because you don't. You got more of those. But you're using more per vehicle. You're going to run out of tires first. And your excess reagent is going to be headlights. Because after you build those 5 cars, you're going to have some headlights left over. Got the idea? Well, it works similarly in chemistry. Let me show you. Let's calculate the weight of nitric oxide produced when 5 grams of manganese react with 10 grams nitric acid. Now, we're not going to worry about the concentration of the nitric acid. We're going to say there are 10 grams of HNO3 that's working for us. Okay. First, perform the calculation with one of the 2 reagents. So I'm going to choose to perform it first with manganese. So for manganese, we have 5 grams times 1 mole of manganese per 54.9 grams. And we're looking for nitric oxide, so we're going to have a 2:3 stoichiometric ratio times, now, NO weighs how much? It's 30 grams per mole. So if we start with the 5 grams of manganese, and if manganese is the thing we run out of first, we will produce 1.8 grams of nitric oxide. Okay. Let's look at the nitric acid. We're going to do the calculation now with the nitric acid. We have 10 grams of nitric acid times 1 mole over 63 grams. And the stoichiometric ratio is 2 to 8. That's right. 2 NOs for 8 nitric acids. And the molecular weight of the nitric oxide is 30 grams per mole. So if nitric acid is the thing we run out of first, do your calculation, then we would produce 1.2 grams of nitric oxide. Now, the answer is 1.2 grams of nitric oxide. Why? Why is this the answer? It's the answer because you're going to run out of nitric acid just as soon as you produce 1.2 grams of nitric oxide. And you will not have run out of manganese because you have enough manganese to produce 1.8 grams of nitric oxide. So your limiting reagent is nitric acid, and your excess reagent is manganese. Got the idea? In this problem, we're being asked to calculate the weight of nitric oxide that could be produced if our manganese, which is 12.3 grams, is allowed to react with 100 milliliters of 20% pure nitric acid having a density of 1.10 grams per milliliter. Definitely a limiting reagent problem. Wonder which we're going to run out of first, manganese or nitric acid? Well, let's see. I'm going to start my calculation with the manganese. I'm going to take this 12.3 grams of manganese, and I'm going to determine the amount of nitric oxide that could be produced if we ran out of manganese first. So I'm taking my 12.3 grams of manganese times 1 mole of manganese, and let's see, manganese has an atomic weight, a gram atomic weight of 54.9 grams per mole, so grams cancel. To find nitric oxide then, I use my stoichiometric coefficient of 2/3, that gets me to moles of nitric oxide, times 30 grams per mole. 30 grams per mole. Moles are going to cancel, and I find this to come out to be, let's see, 4.48 grams of nitric oxide, if manganese is my limiting reagent. Well, let's check. Let's go over here now and work this using nitric acid. And with nitric acid, we have 100 milliliters of a solution that has a density of 1.10 grams per milliliter, but is 20% nitric acid. So we're going to take this and we're going to use 0.200 to multiply that by to get the percent of it. That gets me the mass of nitric acid times 1 mole over 63 grams when I add up the HNO3 times the stoichiometric coefficient now is going to be 2 NOs over 8 HNO3s times 30 grams per mole. And when I work this one out, I find that the nitric acid is sufficient to produce 2.62 grams of nitric oxide. Now, folks, what weight of nitric oxide can be produced? Well, I'm going to run out of nitric acid when I have produced 2.62 grams of nitric oxide. I'm going to run out of manganese when I produce 4.48 grams of nitric oxide. I can't produce 4.48 grams. I can only produce 2.62 grams because at that point I'm out of nitric acid and the reaction quits. So there's manganese left over, waiting to react. What percent, this is a good question, what percent of the manganese was used? What percent of the manganese was used? Well, there's several ways you can go about doing this. There's a harder way and there's an easier way. Isn't that life? Look up here at the equation. Look up at the equation and look at nitric oxide. Do you see that you could start out with nitric oxide? You could start out with nitric oxide right here, and you could take the quantity of nitric oxide that you have, 2.62 grams. I wish you'd quit doing that. And you could go all the way back and calculate how much manganese it would take to do that. Then you could take that weight, put it over the total weight of manganese times 100 and get the percent. But there's an easier way. You see, if we run out of the nitric acid, we're going to produce 2.62 grams of nitric oxide. So 2.62 over 4.48, the amount we would have produced if manganese had been the one to run out, times 100 is going to give us 58.5% of the excess reagent consumed. There's your answer. Think about it. In looking back over this unit, we've talked a lot about calculations. The first that we were concerned with was the mole, one of the most important concepts that you study in chemistry. You must have a good grasp of the mole, and we will develop this concept more in other units. We talked about formulas of compounds from the standpoint of using calculations to determine formulas, and a little bit on the history of how that came about. We talked about calculations from chemical equations. We talked about particularly the stoichiometric ratio. And then we talked about percent yield and limiting and excess reagents. Yes, we did a lot in this unit. A better way to teach and learn chemistry.